In my first presentation, I discussed the vast universe of processors to highlight the unique niche occupied by the microcontroller. For this presentation, we assume that we have determined the microcontroller to be the ideal solution for our design. So what I'll be discussing in this second presentation will be the microcontroller capability, microcontroller pin configuration, and microcontroller block diagram. The idea is that we're going to look at the internals of the microcontroller. We're going to look at the external, which means the pins, and then finally we'll put all together in the block diagram. Before I get started, I would like to note that the information comes out of the ATMEGA 328P microcontroller datasheet. This is a datasheet that you should really download from the ATMEGA database so you can start getting an idea what information you get the first day you buy your chip. So let's go back to the capability. So for the capability, I'm going to be addressing I/O ports, memory, Watchdog Timer, interrupts, analog to digital converter, analog comparator, timer counters, and microcontroller serial communications. Let's start with the I/O ports. The I/O ports, the important thing about the I/O ports is that they can be configured to be input or output. Now the memory. The microcontroller comes with three flavors of memory. You have the 1 kilobytes of EEPROM, 2 kilobytes of internal SRAM, and 32 kilobytes of flash. So basically what you bring is, what you get is a location where you can save your data once the power is off, and also the efficiency of having the SRAM when the power is turned on. Next, let's talk about the Watchdog Timer. The microcontroller provides a Watchdog Timer. The Watchdog Timer is programmed to reset the microcontroller at predefined intervals, and those intervals are known as timeout periods. If the microcontroller is functioning correctly, it resets the Watchdog Timer before the timeout expires, and that prevents the trigger of a system reset. Now, if due to a software bug the microcontroller enters an unexpected state, for example, gets hung up and fails to reset the Watchdog Timer, then a timeout will trigger a system reset. So the idea is that you have your automatic control alt delete. That becomes very useful if for example, your microcontroller is monitor something top of a volcano that is ready to blow up and something goes wrong. Well, you have your automatic control alt delete, which means that you don't have to go up there to try to reset your system. Next, let's talk about interrupts. There are two flavors of interrupts. The first one is the internal sourced interrupt. Microcontroller can be configured to trigger an interrupt based on an internal event. Okay, for example, if you need to turn on and off an LED every 2 seconds, well, in that case, you would set up your timer to trigger an internal interrupt every 2 seconds. Your program would be interrupted, and then it would turn on and off the LED accordingly. Now, the second flavor of interrupt is the external source interrupt. Microcontroller can be configured to trigger an interrupt based on an external signal. So what you would have, for example, if you are hooked up to a sensor that provides data every so often, and if you don't get your data, you will lose it, then you would hook up that external sensor to a pin that triggers an interrupt each time there is some data available. Next, we have the analog to digital converter. Microcontroller again can be configured to read an analog signal such as voltage and then convert it to digital so you can evaluate it. Then you have the analog comparator. The microcontroller can be configured to read two input voltage and trigger an interrupt depending on whether the voltage are the same or are different, high or low. You can set up all those parameters. Now we have timers and counters. The microcontroller provides two 8-bit timer counter and one 16-bit timer counter. Those timers can be configured to count up, count down, or generate a pulse of a predetermined duration. Finally, we get to the serial communication. The microcontroller provides three different serial interfaces. It provides the serial peripheral interface, which is the SPI. It provides an internal integrated circuit, which is the I2C. And finally, it provides a universal asynchronous receiver transmitter, which is the UART interface. Basically, these three serial interfaces are used extensively in industry. So I have here a table to give you a flavor of the differences in these three interfaces. So when it comes, when we're dealing with speed and throughput, the highest speed would be provided by the SPI. Next, a moderate speed would be the I2C. And finally, the lowest speed would be provided by the UART. Now let's talk about number of devices that can be hooked up at the same time. So for the SPI, you can have multiple devices. However, the limitation is that for each device, you need a select line. So if you have 5 devices hooked up, then you need to have 5 extra pins to hook up those cables for the chip select. The I2C, you can also hook up multiple devices. However, they share the same bus because you communicate using the address of each device. So the SPI, you need a chip select, a hard cable to communicate. With the I2C, all you need to do is know the address of the devices you want to talk to. And finally, the UART is a point-to-point communication. Now let's talk about pin count. Like I noted, the SPI requires like 4 cables to establish communication. The I2C, you need 2 cables, and also for the UART it's the same. Now, cable length and noise immunity. The SPI is suitable for short distance and is more susceptible than the I2 and the UART to noise due to the multiple lines that it has. The I2 can handle a little bit longer cable lengths than the SPI, however, and it is built-in noise immunity. And finally, the UART can handle the longest distance of cables. So with this, we're done with the capabilities of microcontrollers. So let's look at the external, the pin configuration. So the chips come in 3 different type of packages. As you can see here, one is the plastic dual inline package, which is the PDIP. Next, it comes in the micro lead frame package, and finally it comes in the thin quad flat package. That's the TQFP. Let's talk a little bit about the PDIP. That's the largest size compared to the other chips. And you can, it's easy to solder manually. It's suitable for prototypes. So this is the kind that you and me would use. We would take it home, we would solder it to different boards and see generate design prototypes. This is ideal for compact design with limited board space due to small footprint. So this is more like if you're going to large production, industry, special machinery for soldering all these things, this is the one you would select. And then you have this one, the TQFP, which offers a balance between size and ease of soldering. So you need a little bit more expertise at soldering than the PDIP, but it's less experience on the MLF. So this is what the chip looks externally. Externally, when you're going to hook up this chip, you are only interested in the pins. Now, how do you know where is pin number 1? The chip comes with a little half circle here that indicates that that's the top, and to the left you start your pin 1, 2, 3, 4, and this has 28 pins. You go 14, 15, and the last pin is on the top, 28 pins. Now for the software doesn't know anything about pin number, but for the software you have, each pin has a name associated with this, and that's what the software looks like. So for us on the outside world, it would be pin 1. For the internal world of the software, this is called would try to do something to the PC6. This would be pin 2. The software would call this PD0, and on and on. So you have the names. Now, each name is associated to a function. So, for example, if you want to do a UART, then you would need the external world. You would have to hook up pin 2 and pin 3, receive and transmit to your laptop, for example. However, for the software, when it comes to configure and putting the data and whatnot, the software would be looking at PD0 and PD1. So when they show you this picture, you have the outside world, the pin number, the inside world name for those ports, and this is the functionality associated. So you have pins, and you have ports, and you have the functionality associated with that. Now let's assume you bought your chip. Now you want to make it work. What do you need to add? So what I show here is I added a 16 megahertz clock plus 2 capacitors, and that's to a ground. Now if you don't add this 16 megahertz crystal, then your chip is still going to work, but it's going to work at 1 megahertz. Now you need to also set up a 10K hooked up to the 5 volts so you can wake up the chip. And finally, you provide power to the chip through pin 22 and 20, which is the 5 volts and the ground. Now this is a practical exercise. So you have a laptop hooked up to a programmer, and then the programmer has to be hooked up to the ATMEGA 328 because we want to load software into the chip. So we would need to hook up the MOSI master out, slave in, and it would be master in, slave out. You have a clock, a reset line in powers. So from so we would look this from a functional point of view. Now from the physical, you would have, now the software functionally would be looking at PB5, PB4, PB3, and PB2 to configure the SPI interface. However, for the hookup, they would be looking at pin 19, 18, 17, and 16. So this actually would work perfectly. Now, so finally we got to the block diagram. This is the block diagram that you have in your data sheet. But if you don't get the background I provided, it's a little bit harder to follow. So here you can see the crystal and the capacitors, and this is the clock generator. Now what you have here is the Watchdog Timer, and of course that's hooked up to the clock because it will get reset, and all that is hooked up to the CPU of the microcontroller, so database. Then you have the analog to the digital converter, the external interrupt, the one of your 16-bit timer, 8-bit timer. That's all up to the data bus that goes to the CPU. You have, like I noted, the EEPROM, your SRAM, your flash memory, UART communication, and your I2 communication. You have your CPU, your bus, and of course this shows the transmit, receive. Now in and out, you have an in and out database here. You have your internal output ports. We've talked about this. Your other clock, your SPI serial communication. So for example, in your SPI you have your Meson, your MOSI, and your chip select. So all this starts making sense. This whole block diagram makes sense now after you've obtained the knowledge of the functionality and the external view of the chip. So that concludes my presentation for today. So we looked at the microcontroller capability, which is the inside capability of inside the chip, we could say. Next, we looked at the outside of the chip, which is the microcontroller pin configuration. And finally, we put it all together in the block diagram. So I hope you've enjoyed this presentation, and next week we'll start talking about the architecture. How do we take all these components and make an architecture so we can start writing our software? Thank you very much.